Okay, let's take a look at this related rates problem. Pause and read the video. Or pause and read the question. Hopefully you've done that. Okay, first thing we always want to do is draw a picture, if it makes any sense. So I've got here on the ground, I've got some dude here. He's right here. He is 3,000 feet away from some tower. So here's some tower. There's a plane overhead. This distance here is 4,000 feet. This plane is going to be going, it's flying this way at some rate. It's moving this way at 600 feet per second. I want to know how quickly is the distance between the guy and the plane changing when the plane happens to be passing over at that particular moment in time. Okay, so let's put the plane here in the middle. Let's say the plane happens to be at this location here. Let's call this distance here, maybe we'll call that X. I can draw in this triangle here. I know this side of the triangle is 4,000. I want to know how quickly this is changing. I want its rate of change, dx dt, when at a particular moment in time, this distance down here, maybe we'll call this d, d is 3,000 feet. Because that's when the plane will be over top of this tower. I could even fill it in my triangle. It might look better if I fill in this triangle. So I've got my guy here. Here's my plane at some time. I'm calling this distance X. That's what I'm trying to measure. And this is how far the plane has traveled since it was over top of the guy's head. When D equals 3,000, the plane is over top of this tower. So that's the moment in time when I'm trying to figure out how quickly this is changing. And I know that this is 4,000. Now, there are actually 3 different ways to solve this problem using related rates. I'm going to do it what I think is the middle way first. Then I'm going to show you a shortcut. Then I'm going to show you a super shortcut that actually doesn't involve related rates at all. We just take a derivative. Okay, how are these related? How are all of these related? Well, I know x squared plus 4,000 squared must be d squared. Or if I take the square root of both sides, so I'm after x here. Oh, no, I lied. X is the hypotenuse. X is 4,000 squared plus d squared. So that's x squared. So x will be, we can't have any negatives, so I don't have to worry about a plus or minus. X will be the square root of 4,000 squared plus d squared. I want dx dt, how quickly is it changing at a particular moment? So we take the derivative with respect to time of both sides. Take the derivative with respect to time. Derivative of x would be dx dt. That's who I'm after. Over here, got to take the derivative. How you take the derivative of a square root? Think of this as 4,000 squared plus d squared to the 1/2 power. So the 1/2 comes down. 4,000 squared plus d squared to the negative 1/2 times the derivative of what's inside. Derivative of 4,000 squared, that's just a constant, that's 0. Derivative of d squared will be 2d times d dt. I know that looks weird, d dt. You just got to understand from context what that means. d here means this distance. I could have given it a different name, but I wanted this to happen on purpose because this happens sometimes. d dt means how quickly is this length right here changing per second. And I actually know that. That's the speed of the plane. So note that d dt is 600 feet per second. It's measured in units of distance divided by units of time. So I want dx dt. I want this evaluated at when d equals 3,000. So now we just plug everything in. So dx dt will be, I'm going to rewrite this. Notice first off, the 2's cancel. I get d over square root of 4,000 plus d squared times d dt. So plugging in all of my values, I know d, the moment I'm interested in, is when that's 3,000. So I plugged in 3,000 for all my d's. And then this is how quickly is d changing. That's the speed of the plane, 600. Now, this is a Pythagorean triplet. Like you could check this on your own. That's a 3, 4, 5. So that this actually simplifies to 5,000 squared. Square root of that is just 5,000. Let me make all this smaller. So what we actually get, you can, again, check this on your own. This is just 3/5 times 600, which is 360 feet per second. We got always have units on here. So that's how quickly the distance between our guy and the plane is changing. Not always, but at the moment the plane passes over the radio tower. Okay, now here's a different way we could have done the problem. Like I said, we're going to do it 3 different ways. From right here, once I had this relationship, I had x squared equals 4,000 squared plus d squared. I went through the trouble of solving that for x, but I didn't have to. Once you get a relationship between your variables, just take the derivative. Just use implicit differentiation. Take the derivative with respect to time of everything, keeping in mind that all your variables depend on time. So derivative of x squared is 2x times dx dt. Remember, we're using implicit differentiation. Everybody here depends on time. 4,000 is just a constant. His derivative is 0. Derivative of d squared will be 2d times his derivative, d dt, even though it looks weird, d dt. Now, look what I got to figure out. So I know d, I know that. That's 3,000. I know that. That's the speed of the plane. That's 600 feet per second. This was feet. This is what I want. I just got to figure out X. So I still need, if I'm going to do the problem this way, I need X, not always, but at a particular moment. When? When D equals 3,000, the moment I'm interested in. But that's pretty easy to find. I can just draw out my triangle here. When this is 3,000, this one's always 4,000. This was X, just Pythagorean. And again, you can check this on your own. This is a Pythagorean triplet. This will be 5,000. So A squared plus B squared equals C squared. So when D equals 3,000, X is 5,000. So I get 2 times 5,000 dx dt, the guy I'm actually interested in at this particular moment. In fact, look, the 2's just cancel. We don't even need to worry about that 2, right? That'll equal 3,000 times d dt. Well, I know that. That's 600. So I get dx dt equals 3,000 divided by 5,000. That's just 3/5 times 600. Oh, I got the same answer I got before. That's lucky. Okay, there's a second way. Here's a third way. And honestly, I think this might be more work, but what we could have done right at the beginning is think about this distance here. Write that as a function of time. We could actually write out D. So, or that's just how far the plane has traveled since it was over our heads. Distance equals rate times time. I know how fast it's moving. It's going at 600 feet per second. D as a function. So D as a function of time is just 600 times time. Rate times time. Distance equals rate times time. That's of. So back up here, that would mean X is square root of 4,000 squared plus 600t squared. And now there's no implicit differentiation, at least on the right side. This is a function of time. So just dx dt, it's just take the derivative, dot, dot, dot. You literally just take the derivative with respect to time, but now you would have to find that time. So I would get that at t equals, see, now I got to do some work. How long would it take? If I'm going 600 feet per second, how long would it take me to get 3,000 feet? That would be 5 seconds. So I just divided 3,000 divided by 600. So we could explicitly write out X as a function of time. We literally know the formula for X here. And then take the derivative. We got to solve for the time. So plug in the time into the derivative. And like you could check this on your own. You would get exactly the same thing. I think this is more work, but it is sometimes possible in related rates problems to the thing you're looking for to actually find a formula for it that has t in it, solve for t, plug it in, you're done. Usually it's much easier just to use implicit differentiation and relate 2 different rates together. Okay, that's a good place to stop on that one. That was a challenging